Math 2415, Chapter 10, Vectors in the Geometry of Space, Section 2, Vectors, Video 2, Vector Operations with Arrows. In the previous video, we introduced the concept of a vector and the idea that we can represent it with an arrow connecting an initial point and a terminal point. In this video, we're going to learn about how you perform operations on those vectors. And by operations, I mean something that will take one or more vector and turn it into a new vector. We're going to start with vector addition. Let's just jump right into it. Let's say we have a vector u that looks like this, a certain direction and magnitude, vector v that looks like this, a certain direction and magnitude, and we want to add them and find the sum u plus v. To add two vectors visually, you have to imagine where they would put you collectively if you followed where they pointed back to back. In other words, you can do what's commonly called tip to tail. If we start by drawing vector u, and I'm going to try to draw it with the same magnitude and direction as I have up here, you can think of it as what's called a displacement vector, a vector that takes you from one location to another. The sum of the two vectors is just the net result of doing these two displacements back to back. In other words, after we displace the initial point along the vector u, we immediately follow it up with vector v, which looks about like that. So think of it as a journey consisting of two steps. Let's travel where u tells us to travel, and then let's travel where v tells us to travel. The sum of the two vectors is the net result, starting with the first initial point and concluding with the second terminal point. The vector u plus v would be right here. So again, if you think of a vector as a motion, as a displacement, if you will, the sum of two vectors is just the net result of those two displacement moves back to back. Now, there's two ways to visually think about how to represent the sum of two vectors. One is called the triangle rule. The triangle rule simply says that you put the initial point of the second vector on the terminal point of the first vector, and then the sum is the vector connecting the initial point of the first vector to the terminal point of the second vector. In other words, the total result, or the total displacement of executing these two individual displacements back to back. But there's also a rule called the Parallelogram Rule. The time for the Parallelogram Rule is when you have two vectors but they have the same initial point. For example, let's say we had vector u, which again I'm trying to make it as consistent as possible with that one, and we also have vector v, but vector v initiates from the same initial point. So right about here. If the two vectors you're adding have the same initial point, connecting their terminal points would not give you their sum. If I connected these two terminal points, I'd get a vector pointing kind of down, which is not the same as the vector over there. So how do you find the sum when your two vectors visually have the same initial point? The answer is you draw the diagonal of a parallelogram. What parallelogram? Well, think of these two vectors as being half of it. To locate the other half, you simply draw v on the terminal point of u, and you draw u on the terminal point of v, completing a parallelogram. The sum is the vector that connects the common initial point with the common terminal point at the end. And if you'll notice, the parallelogram rule is really just the triangle rule with twice as much drawn, or the triangle rule is really embedded inside of the parallelogram rule. But either way you want to think about it is fine. I would be familiar with both and understand the difference between the two. The triangle rule for adding vectors says if you draw the first vector and then draw the second vector so that its initial point coincides with the first vector's terminal point, then the sum is the vector connecting the first vector's initial point with the second vector's terminal point. The parallelogram rule says if you're finding the sum of two vectors and they share an initial point, then at the terminal point of the first vector, construct the second vector, and at the terminal point of the original second vector, construct the first vector. The sum is the diagonal of the parallelogram that connects the common initial point with the common terminal point. Personally, I think the parallelogram rule is a little redundant, because once you draw half of the remaining parallelogram, there's no need to draw the other half. In other words, the minute I drew the v vector following the u vector, I really didn't need to draw this fourth side, because I could kick into the triangle rule and just go ahead and draw the sum of the two vectors. The triangle rule is also called tip to tail, where you put the tip of one vector on the tail of the other, and then the resultant, which is also another word for the sum of two vectors, resultant, is the same as the sum. The resultant is just the one vector that completes the journey in one move. Instead of going up and down, just go straight across, or wherever it is. The other vector operation we're going to talk about is called scalar multiplication, but in order to talk about it, I have to define what I mean by a scalar. A scalar, to contrast it with a vector, which is a quantity with both magnitude and direction, a scalar is a quantity with magnitude only. With magnitude only. So in other words, it's a number, but no certain direction. For example, 5 miles is a scalar. 5 miles north is a vector, because it has magnitude and direction. But what do I mean by scalar multiplication of a vector? Well, it kind of makes sense if you remember that multiplication is just a form of repeated addition. For example, if I ask you what 3 times 4 is, you could just add 4 3 times. So if I asked you to sketch the vector 3u, that's the same as u plus u plus u. Meaning that I could just take this vector, put 3 copies of it back to back, and 3u would be the sum of all 3 of those. Another way of thinking of it is scalar multiplication scales the vector by changing its magnitude but not its direction. Think of it as stretching this vector 3 times as long as it originally was. There's 3 copies of u back to back to back, and so the vector 3u would be the vector from the very beginning to the very end. In fact, the word scalar was chosen because its root word is scale, meaning to basically dilate it or either make it larger or make it smaller by zooming in and out. Think of zooming in and out like with the camera. When you zoom in, it makes it look larger. When you zoom out, it makes it look smaller. You're adjusting the scale via the scalar. Scalar multiplication really isn't that hard to visualize. When it comes to fractions and decimals, you just have to be a little bit careful. For example, if I wanted to draw, I don't know, 1/2 u, then I would take a u vector and then draw 1/2 as short, and that would be 1/2 of u. But if your scalar is negative, not only does it scale it, but it changes the direction into the opposite direction. So for example, let's say I wanted to draw negative 2v. And v was, well, it's gone now, but v is this vector. To draw negative 2v, I would have to figure out what 2v is, but then change its direction. Or change this guy's direction and then take 2 copies of it. If this is v, negative v has the same magnitude, but the opposite direction. So negative 2v would be 2 of these. This one vector would be negative 2v. So scalar multiplication changes the magnitude, and if it's negative, also points it in the opposite direction. The last vector operation I want to talk about is subtraction, but honestly, subtraction is just a culmination of addition and scalar multiplication by -1. Meaning that if you have something like u minus v, then that's just the same as u plus negative v. So let's see what that would look like. Here's u, here's v. What would u minus v look like? Well, minus v would take the v vector and reverse its direction, And so for u minus v, I can now treat it as u plus negative v. Here's u. Negative v goes back this way. And then so u plus negative v would be the sum of those, or just u minus v. So you can treat it like vector addition, you just have to reverse the direction of the second vector. There is a way to sketch the difference of two vectors without physically reversing the second one. And the way to do that is if they have a common initial point. So for example, let's take that vector u, and let's take vector v here. If you're going to find the visual representation of the difference of two vectors and they share an initial point, you can actually just connect the terminal points. Now, not when you're adding, but when you're subtracting, you can just connect the terminal points. Now, the direction that you connect them makes a difference. For example, let's say I connected from the terminal point of v to the terminal point of u. That's going to be the difference of these two vectors, but in what order? It's going to be u minus v, and here's the reason why. By drawing this vector that connects the terminal points, you just completed an addition problem. The addition problem is v plus this is equal to u. V plus this vector is equal to u. So whatever this is, I have to be able to add to v and get u. Well, if I want to add v and get u, I have to put something that cancels the v and something that brings in the u. So connecting the terminal point of v to the terminal point of u gives us the vector u minus v. If I were to have connected it in the reverse direction, from the terminal point of u to the terminal point of v, the addition problem that I'm completing is u plus something is equal to v. So whatever I add has to cancel the u, and hence have a minus u, and bring in a v. Connecting the terminal point of u to the terminal point of v gives us the vector v minus u. Now all of these are assuming that u and v have the same initial point. Just remember, when it comes to vector addition, the sum is the result of doing back-to-back displacements, and then the sum is from the first initial point to the final terminal point. And by the way, you can do this with more than two vectors. Scalar multiplication just simply says stretch it out farther, and if it's negative, turn it around. For subtraction, it's just the adding the opposite. Or if your two vectors have the same initial point, then it's just a matter of connecting the terminal points, but the order doesn't matter because subtraction is not commutative. Keep walking that way to end the video. There's a cord dragging that I can't step over.